The subject of this overall module is Fourier series, and actually it's broader than that. It's actually orthogonal expansion, of which the Fourier series is one example, or I should say the Fourier series as you probably know it. So I'm going to ultimately talk about orthogonal expansions and then show it being applied to Fourier series as you know it. But the way I'm going to do it, we need to talk about complex numbers. So I need to take a little time, this one little recording, to just kind of give a review of complex numbers. You might think you know it, maybe you do. But when I've taught this and other courses, I find that a lot of students are more rusty on complex numbers than I would have thought. So let's review some of that. First, here's super basic. Here's what a complex number is. It's a plus ib, where this I is this imaginary number, the square root of -1. Here, a and b are real numbers. And I introduce complex conjugate notation here with this overhead bar. And it means flip the sign of the imaginary part. If a number is real, this b part is 0, and the complex conjugate is just the original number. Now let's get into more fun stuff about it. Start thinking of complex numbers as being in this complex plane. We have the real axis being the horizontal axis. The vertical axis is the imaginary axis. Say I've got this complex number a plus ib. That means it's over a along the real axis and up b along the imaginary axis. So here's where that complex number is. I can express that in polar coordinates. In effect, this is the rectangular coordinate way to express a complex number. I can express it in polar coordinates as a magnitude or a distance from the origin and an angle up from the real line. Well, let's derive that really quickly. This complex number would be this rho times cosine of this theta plus rho times sine of that theta here. So I just re-expressed that complex number. But I can factor out this rho here, and I'm left with cosine theta plus I sine theta. We have Euler's formula, which says that is e to the I theta. So we can express the complex number this way. Rho e to the I theta. Call that phasor or phasor format. It's really the polar coordinate version of the complex number. And you can do the trig to find things. You know, the magnitude, this rho is just a squared plus b squared. The angle would be the inverse tangent of b over a, that sort of thing. By the way, where's the complex conjugate? It would be down here. Just flip it around the real axis. It's the mirror image around the real axis. So in angle format, it's the same rho, but the negative angle going down the same theta. Or in rectangular coordinates, it's the same real part, negative of the imaginary part. So that's what complex conjugate means geometrically. I'm not going to explain everything on this chart. Don't be too scared. So here's a complex number, rectangular coordinates, phasor form. Complex conjugate, you just change the signs in the I parts. And we can do some manipulations. First, I'm introducing some notation here. These things that look like absolute value signs mean the magnitude. So the magnitude of a product just use these definitions, ends up being the product of the individual magnitudes. Here's some more notation. Angle. This theta is called the angle of this complex number. Anything that's not the I up here in the exponent is the angle. So the angle of a product is the sum of the individual angles. If I take a ratio of two complex numbers, the magnitude of the ratio is the ratio of the individual magnitudes. And the angle is the difference of the two angles. These are all simple to derive. You might have some fun with complex numbers doing some of this yourself. Be a good exercise. Some special features of doing something with a complex number and its complex conjugate, its conjugate pair. If you add two complex numbers, you get an all real number that's just twice the real part of the original number. Subtract the complex conjugate of a number from the number, you get a purely imaginary number that's twice in the imaginary direction of the original number. Multiply the number and its complex conjugate, you get the squared magnitude. I'm not going to go through all this. Let's see. The complex conjugate of a product is the product of the individual complex conjugate. We'll kind of use some of these, some more often than others. I think that's enough. Oh no, we got some more stuff to go through. So let's look at just the e to the I theta stuff. First, this thing, e to the I anything, has a magnitude of 1. Meaning in the complex plane here, e to the I anything is somewhere on this unit circle. I didn't quite draw it symmetric, but this is supposed to be the unit circle. So what is this point here? It's on the real axis, the right one. It's just the number 1. This number over here is the real number, -1. This number up here is the purely imaginary number, I. And this number down here is the purely imaginary number, -I. Now look at some angles. And that's what I've written out here. Over here, the angle to this point is 0. So e to the I 0 is 1. If I go up, here's 45 degrees, here's 90 degrees, that's pi over 2. That's the purely imaginary number, I. E to the I pi over 2 is I. If I went down minus pi over 2, I'm down here at minus I. If I go to an angle of pi, pi is 180 degrees. I'm going from here over to here. E to the I pi is -1. If I just go all the way around 2 pi, I'm back at 1. E to the I 2 pi is 1. And I could keep going around a whole bunch of 360 degrees or a whole bunch of 2 pi's. Integer number of times, I always get back to 1. So e to the plus or minus I 2n pi is 1. I just go an integer number of pi, I'm going from here to there, back to there, just oscillating between +1 and -1. Here's the formula for that. It's easier to think of where things are on this unit circle than to memorize all this. But here's some of those identities. The Euler's formula can go the other way. You can express cosine in terms of these phasors and sines in terms of these phasors. And since they look so close and We're going to talk about them a lot more later. These are the hyperbolic trig functions, cosh and sinh. They look like cosine and sine in Euler format, but there's no i's in them. It's all real numbers here. We'll talk more about them later, but I thought I'd at least introduce them here. So I think that's the basics we're going to need to talk about the rest of this module. So let me do that in future recordings.